Good morning. How's everybody? Sorry for my tardiness. I went to the wrong classroom. It's terrible. Yeah, I know, right? Jeez. Still though, I apologize. So, so we have been toying around in assembly land for a little bit now. Hopefully we can close the topic off today. We really only have one more thing to talk about, and that is how to load and unload memory. We're going to be talking about sort of, in the context of visual, of course, it's not real, well, I mean everything's in real memory, but you know, they're emulating the RAM that you're interacting with in the same way that you're emulating everything else about everything in visual. So the address numbers are not going to look real, but you know, it is what it is. So we're going to learn how to declare and initialize regions of memory, find the addresses of declared memory cells, load data from memory into registers, and then put it back again. So, in order to declare memory, we have a new special instruction, DCD. Actually not sure what it stands for. Disco Convention Disaster. These are assembler directives and are not directly instructions for the CPU. This is a directive which is set up. It's kind of in the same vein as a type def, but basically you're just declaring some memory in the main memory unit and initializing it with the values given. So you may declare either a single element or a sequence of elements. My var is a declared variable. Array is a declared array. The numbers you provide afterwards initialize the memory. These variables may not be used directly to access the data within. There is no in-place dereferencing operator. So these guys are not variables in the same, like you can't just use them in expressions like they're variables, right? You have to go through the pointers. Like you have to manually do the dereferencing operations because, you know, that's one of the things that's provided by default by C and other programming languages. When you use a variable, it's dereferencing it for you automatically. You don't even have to think about it. But in assembly, you have to think about everything, painfully in excruciating detail. So, in order to load data from a declared memory region into a register, you need the following operations. First, you need ADR, which of course stands for address. ADR looks up the memory address of the variable specified and stores it into the register specified. The ADR command is equivalent to C's address of operator, but of course storing the results in the first operand, as is normal for assembly coding. In this case, we are storing the address in R1. The LDR command loads the data at the address specified by the second argument and stores it in the register specified by the first. So, LDR is load register. Load into register 2 the thing stored at the address in register 1. So, in this example, my var, which has a value 77, will be loaded into R2. The square braces around R1 are the equivalent to C's dereferencing operator star. So, that right there is a pointer dereferencing operation. So far, so good? Any questions? Storage, very similar to loading. Storing memory from registers into memory requires but a single instruction. This is not the strength stat, this is the store operation. The only catch here is that the operands are in the reverse of their usual order, so we are going from R2 back into R1, not storing in R1, or storing in the first operand. This means that in order to write data into memory, we need to either dedicate a register to holding that variable's memory address, or we need to keep reloading that address using the address of operator. Normally, you just keep the address in memory. That's why you have 13 functional general purpose registers. Make sense? Shall we do an example then? So, we're going to do a suitably complicated example. Let us consider the problem of taking the sum of an array. We will make the following assumptions. Number one, we wish to sum an array that has been declared in the assembler directives. So, no reading outside data. The size of the array we are working with is also stored in this declared memory. Note that it is the size of the array in bytes. So remember that lovely thing where C would calculate memory offsets for you based on the data type of the things that you were using pointer arithmetic on? Well, that's another thing that you have to do yourself now. Isn't assembly programming wonderful and lovely? So, when we say size in assembly, we are saying the size of the array in bytes, not in elements. Since these are, so basically these are all assumed in that case to be how big? Merrick?
4 bytes?
4 bytes, thank you. What's 20 divided by 5? Right. Question? No? Okay. Furthermore, we want to store the result of our calculation back into memory, so we are dedicating a piece of memory to storing the result. Next, we need to decide what our registers are going to be and do. So, R1 will be the memory address of the array, since we need it to, throughout to access different addresses, right? Makes sense to keep the array, the address of it in memory. R1 will be the size of the array. Since we only need this value to be set once, like the const parameter, we don't need to maintain the memory address of size. That makes sense, right? We only need to read the size at the beginning once. We don't need to modify it later on, and we don't need subsequent accesses. So we don't need to keep the address. To compute the sum, we'll need an accumulator and a counter, so let's make them R2 and R3 respectively. And to store the result, we'll need a register for the address of the memory cell we wish to store the result in, make that R4. Although, by the time we have finished calculating the sum, we could very easily repurpose one of the old registers to perform the output of the result, as long as it isn't R2, because that's the thing we're going to be keeping the sum in. Make sense? Question?
On the previous slide, we used DCD to create an array and then also declare the size. But then for result, how does it know if you're doing size or if you're actually putting an integer?
It doesn't. It doesn't have data types. Things only have data types insofar as you apply the correct operations to them. If you apply floating point operations to them, they're floats. If you apply integer operations to them, they're integers.
And how do you know that it's the size and not integer?
Because you use it consistently that way. There's nothing in the program preventing you from mucking up. It's programming without the safety net. Insofar as C is programming without the safety net, assembly is programming over a boiling pit of lava. Any other questions? So, so here is our suitably complicated example. Here is the setup portion anyway. So, after our declarations up front, we store the address of array and size into R0 and R1 respectively. Then we load from the address at R1 into R1, thus overwriting the address that we found in the previous instruction. Remember, this is the size. We said we only needed to read it once, so we're only reading it once. We are initializing R2 and R3 as the as the accumulator and a counter respectively, and we are storing the address of the result in R4 so that we can use it at the end to store the result in. Yes?
The octothords before the 0 that you can
Yes, those designate integer literals.
What if you didn't have
It would be an error. You don't need them here because this is an assembler directive. It's not an assembler instruction. But if you have the octothorpe character, this means the number 0. It designates it as a literal. I know, once again, you know, we're all used to being coddled by C, and you know, we're used to the idea of being able to use a literal without having to say to the program that it is a literal. Well, that's another thing that you don't get in assembly programming. So the boiling pit of lava also has lava sharks.
Like it's easier to say when you do that.
I mean,
Basically nothing.
basically nothing. You get CPU instructions. And oh yeah, they're going to expect you to like. Last year I taught 2TA4. I'm kind of glad I'm not teaching it this the next semester. It's pretty bad. Just, you know, on the DL, just between me and you, it's bad. Like the stuff on assembly, like it's, especially considering it's like at the second year level, and I'm not sure how much Dr. Bokhari is gonna like modify it. I've pointed out the issues to him with it, but like it's you're gonna be trapped in bit hell for a semester basically. Yeah, you want to see some of the slides? I've got some of the slides. This might be more informative actually. Let's see here. Preview of coming attractions. Let's see here. So, let's see here. Where's a good slide?
Is that your next semester?
There we go. Oh yeah, you know this calculate the sum of an array thing? Well, you know, here it is in assembly. Yeah. And then, like, for some reason, the slides expect you to understand where it's stored in an ARM processor, how it's fetched into the CPU in an ARM processor, how it interacts with its peripheral memory, what the addresses of the peripheral memory that it's interacting with are. It's intense. It's very intense. It's just intense. There's a lot of stuff going on. You know, all this stuff that I'm like kind of doing in like big blocks on the chalkboard. It's like, this is what an ALU is. It's like woof. Yep. So oh yeah, here are your registers, etc. etc. And this is like the second set of slides. Yeah, it gets particularly bad in the third set of slides where you start trying to use these for general purpose I/O. Yeah, so in ARM architecture, in order to, for example, set the output bit of a particular general purpose I/O pin, you have to be able to set a specific bit inside of a particular register with a particular memory address to a particular value, and that's how you do it. So, you know, the labs use C, which is a mercy, but the labs are also very, very thick, and not exactly designed for beginners. So, difficult to understand. Is there anybody in the room who's used ARM, who's programmed ARM chips before? The only saving grace last semester was that there were a few students in the class who had and saved the butts of everybody else in the class. So hopefully they're just not attending the lecture today and you have a couple of them. I understand these are dire warnings, but you know,
No.
preview of coming attractions. You shouldn't be smiling, come on. Okay, so, getting back, come on, let's get back. So this is just the preamble, right? This is just the initialization phase. This block of 6 lines of assembly instruction is basically the equivalent of setting all of your variables, right? Not that variables exist. Could you please try to keep it to a dull roar in the front row? Thank you. That's why the back of the room is provided if you want to have a conversation. So, once our registers and data are set up, we can proceed to the meat of the algorithm. Fundamentally, to compute the sum of the array, we need to loop over the array until the maximal element in the array is reached. In C code, this is relatively simple. Bing, bang, boom. We know how to increment I using add, test the condition I is less than size using comparison, and create the loop itself using b plus some condition code. What we don't know how to do is read the elements of the array. Because the elements of the array must be loaded from memory, we must use the load instruction to do so. You can use register, comma, offset to dereference memory, dereference a memory address with a given offset. So, basically you use a comma instead of a plus, and things work reasonably well, reasonably similarly to C with the dereferencing operation, right? The only trick, of course, is that offset must be given in bytes. The offset may be a register or a literal, but in this case we'll use a register because, of course, we are trying to iterate through the array. The counter variable is counting a number of bytes that we are counting through the array at, right? So that's the offset that we're going to be using to calculate the position of the array that we're dereferencing. Make sense? Or that we're loading from. If we put that together, we get the following. So load into R5, R0, R3. Notice that we've introduced a new temporarily used register for this load operation because we can't load the number directly into the sum we're calculating. That would overwrite the sum, right? We have to load it somewhere else and then add it to the sum manually, right? So in addition, R2, R2, R5, add operation. That adds the value loaded from the array with offset given by R3 into the sum that we're computing. So that all told implements sum plus equals array at I. Make sense? No? Yes?
How do we implement R3 to keep track of offset?
Right here. So the question is, how do we increment R3 to keep track of the offset? The answer is once per loop execution and by adding 4 to the value, which is, of course, the size of the things that we're adding together. Right? So if we take all of this and we put it together, we've got our initialization phase. We've got start tag, which is unused but still useful to designate things. We have our initial setup of our registers, previously discussed. Then we have our loop logic. So in our loop, first thing we do is we load the array plus offset into R5, as previously stated. We then compute R2 plus R5, storing in R2, pardon me. We then increment R3 by the size of an integer using add, compare R3 and R1, compare the index with the size. Then we branch on less than back to the loop. Repeat the loop if I is less than size. Right? That traps us in the loop until I has reached size, at which point we enter the finished phase where we store the result calculated in R2, which is the sum that we've calculated so far, into R4, or the memory address. You dereference R4, find the memory address, and put the result in there. Then we end. There is actually, incidentally, a dedicated end opcode. So you can use that, or you can just let the thing run out. Yes?
How does it know like how many bits a number is? Like we're saying.
You tell it.
Right, but like we're saying the offset is R3, so it's like 4 by 4. But then isn't that just the first bit? Like how does it know to read the next 4 to make a number? Or like with the brackets, like how does it know R4 is 4 bits worth of information?
ARM is 32-bit architecture.
So it just
Yeah. So it's 32-bit like these are 32-bit add operations. So if you want a more complicated add, like a floating point add or something, you would have a different opcode. It's baked into the codes themselves. Yeah. Did you have a question?
I was just gonna say, like, it basically knows that it's gonna be operating on integer literals that are 4 bytes.
Yes. Yeah. Yeah. It's built right into the CPU instruction.
So is there like a separate add command if you wanted a longer data type?
Yeah. Or floating point add also looks different, right? So, yes. I'm not sure that Visual even supports floating point operations, now that I think about it. Question?
How would you import the number? How would you display it?
You'd need a terminal, right? Like what are we even displaying it to?
So are there commands to be able to
The reason that Visual operates as a debugger so that you can see the state of the variables throughout execution is because you basically don't have print statements either. Any other questions? Yes.
There's no pre-signature. Can you like upload like letters using assembly, or is that for example? It's like hello world, for example. If you want to do hello world.
I mean, it certainly is possible in a full-blown ARM, processor, but at the moment I'm just trying to teach you the math carrying subset, if that makes sense. Characters are just binary data anyway, right? To operate on characters instead of integers, you would swap this to a 1 because they're single bytes. Assuming you're working in ASCII, 2 bytes if it's Unicode. Yes.
And how much depth will we see assembly on the exam?
If I'm feeling ambitious, there might be a couple of multiple choice questions.
But we will not be expected to like actually program into assembly.
In previous years, I certainly would have expected you to program in assembly. This year, I do not have any TAs to mark such questions, and no auto grader exists for it because it's a much more complicated problem, auto-grading assembly code, then basically we'd have to build our own assembly interpreter and, or, take this one, rip the guts out of it, and throw an autograder in it. But I don't have any way to mark it.
What if the TAs come back before the exam?
I still have to design the exam now, and the exam has to be set before the exam period starts, which means I have to write them now as if I didn't have TAs.
Understand?
So that's how it goes. Question?
Would the multiple choice be more along the lines of like asking about the rules, or would it be like, oh, here's this assembly code, can you tell like what lines are there in error, or like what would the output be, like what kind of multiple choice would you expect?
I mean, I don't know, I haven't written them yet. No. Something like, when you're studying, study the slides. Yes?
So again, like how about like our last assignment, so we're supposed to do like the assembly test results?
I certainly encourage it for practice, but they won't be marked.
Okay, now all we need to do is just like first two structural questions.
Yeah, just do the C programming questions, those are going to be marked eventually. But the assembly coding stuff, I have no way to mark it, so, yeah. And if you feel that this is not the education that you're paying for, I strongly encourage you to send a letter to the university administration asking them to offer the TAs a fair deal. Or send a letter to the union telling the TAs to stop whining. Whichever of those two, whichever side you think that you fall down to in this conflict, I mean, in reality, probably, like, most problems are met in the middle, right? There's whining on one side and there's being rapacious bastards on the other, so. Ooh, that could be our word of the day. No, rapacious. You've all heard the word bastard. I'm sure you use it a lot behind my back. There. So, rapacious. Clawing, greedy, avaricious. Synonyms. So, anyway. So, I guess we'll just, we'll run this bad boy. You can see how it works. There we go. You'll notice that this has some of the redundant tags thrown out and far fewer comments. So, in Visual, when you are operating with the exterior memory unit, it's very useful to be able to see what's going on in there. So you can view memory contents by going Tool, View Memory Contents. You have to actually execute it first, but you'll notice that we have a series of word addresses. We have a series of values in the 4 bytes contained in each of these word addresses and a value associated with all of those. Of course, it will make more sense if we view things in decimal rather than hexadecimal. So, our array 10, 20, 30, 40, 50, 10, 20, 30, 40, 50, our size 20, and you'll see this is after execution. So the result, which was 0, has now been calculated as 150, which if, the more mathematically astute of you might be able to instantly realize that that is the correct sum. So let's step backwards, forwards, backwards. Yes. I guess I just have to view the history then. So, R2 is our accumulator. You'll see that on line number 10, it's initially set to 0. On line 15, it adds up the accumulated sum, right? We'll notice that, oh, actually, here. Yeah, this is good. So, on line 6, we are taking the address of size and storing it in R1, and then on line 8, we are loading from that address into R1, and the load value is hexadecimal 14, which of course is in decimal 20. So, if we take a look at our memory contents, you'll notice address hexadecimal 114 is in fact the one that we're loading. Make sense? Everything works. Any questions? Okie dokie. So, quick note on indexes. I've already talked about it, but let's go over it one more time. Note how we are incrementing R3 by 4 on each iteration. In C, we don't have to worry about the data width of the elements of our array. This is taken care of us by the type system. You may have noticed that assembly doesn't have a type system. There are no types at all. This means that we have to manually align our pointers to the words in memory. Huzzah! Since integers are 4 bytes in size, we can increment by +4 rather than +1. Sorry, we increment. It's not can increment. We must increment. The memory map can verify for you what your word size is for a specified operation. Any questions on assembly programming? Area 1. Forever alone is the correct reaction to anybody who programs in assembly for a living. Like, my God. So I made a solemn promise. I don't know if I told you guys about this, but I made a solemn promise to the professor who's teaching you guys data structures next semester that I would at least do a little bit of C++ with you before letting you go. So we're going to do a little bit of C++. Again, please pay attention, because this is the language you'll be expected to use to do your algorithms course next semester. So, how many people have used C++ before? Alright, you can leave. Except you, you're holding the camera. I'm probably not going to be saying anything you don't already know. How many of you have programmed in Java? Alright. For you guys, this is probably going to sound more familiar, but with more clunky syntax. A lot of the concepts will carry over from Java into C++ and back again. They're very similar languages that were developed at similar times and serve similar purposes. C++ is more efficient though. So, one second, I have a thought that I want to express to all you Java programmers out there. So you know how Java uses the Java virtual machine as the interpreter, and that means it can run on anything you have a JVM for, right? If you take that out and replace the C, the C approach to compilation, right? Which is to say, this is not running inside of a virtualized environment. It's not running in an interpreter. It's being compiled down to machine code and being run bareback on the CPU. That's C++, right? So very, kind of a similar idea to C. This is why C++ is more efficient than Java, because when you introduce the JVM, you are necessarily introducing some overhead. C++ is basically as close as you can get to C with classes, but still, almost as fast as C. So it's a good language for speed, but it's difficult to program. So, how to learn C++ in 21 days. Days 1 to 10. Teach yourself variables, constants, arrays, strings, expressions, statements, functions. Days 11 to 22. Teach yourself program flow, pointers, references, classes, objects, inheritance, and polymorphism. 22 to 697. Do a lot of recreational programming. Have fun hacking, but remember to learn from your mistakes. Day 698 to 3648. Interact with other programmers. Work on programming projects together. Learn from them. Teach yourself advanced theoretical physics and formulate a consistent theory of quantum gravity. Teach yourself chemistry, molecular biology, and genetics. Use knowledge of biology to make age-reversing potion. Use knowledge of physics to build flux capacitor, to go back to day 21. Replace younger self. And that is how you can learn C++ in 21 days. I thought that was a good comic, so I read through the whole thing. So, let's talk about the C modernization project, which occurred, of course, in the mid to late 80s. So, only slightly less modern than when C was, or slightly more modern than when C was first developed. But anyway, so the original designers of C did not expect it to become so popular. It was kind of like, how Tamagotchis just exploded despite the fact that they're really not that great as a toy, They're like, they were in the right place at the right time with the right set of features. C was the Tamagotchi of programming languages. It just exploded in popularity. Nobody even understood why at the time. So, the C language quickly became entrenched so that only so much could be changed to maintain back compatibility. Yet the language had flaws, as I'm sure all of you are painfully aware. In 1979, Bjarne Stroustrup began developing C with classes at Bell Laboratories. By 1985, this program had become C++. The ++ is a reference to the increment operator in C, indicating C as the new and improved C. Incidentally, y'all wonder where C# got its name? It's C++++, yeah, C++, and then C++++ is C++++ equals C#. That's where the name came from. So you gotta hand it to the lads. They have basically 3 molecules of creativity combined, but they're good programmers. So the design philosophy of C++ was to take C and integrate more abstract language features to make it less of a pain in the ass. To be properly studied, C++ would require its own course. It is an elegant weapon of the more civilized age. So this is from a couple of years ago. Incidentally, my most hated, I think I showed you this in class, my most hated language is now the #1 frigging programming language in the world. But C++, you can see, has been relatively popular for, 20 years. Certainly occupying the 4th, 5th category at intervals, sometimes swapping with VB and sometimes swapping with, what's this purple one? It's, C#. C# you can see is peaked in popularity around 2012 and has since been declining. But if you take a look at the latest TIOBE index, C++ is on the rise again. So there you go. So at this point, you may be wondering how applicable your now perfect and impervious knowledge of C programming is to C++. Sorry, was that a joke?
No.
No, good. And that's the attitude that you should have as a professional engineer. Just kidding. That's the opposite of what you should think. But anyway, so C++, this is a very important point, C++ is a superset of C. All C programs are valid C++ programs, but not all C++ programs are valid C programs. C is a proper subset of C++. That means whenever you are in a bind and you can't figure out how to do something in C++, you can always fall back on C. Right? It will always be valid syntax. Yes?
Does it have different syntax? Like, like for example, like printf, is it applicable in C++?
Yes. C++ has printf, but they prefer you not use it.
Isn't it like cout or cout?
Yes, yeah, we'll see an example of it. STD cout. They prefer you to use it this way because they prefer you to use the IOStream library, but there's nothing preventing you from loading our good old friend stdio.h and using printf. Nothing preventing you from doing
If
that.
we loaded both, like the stdio and the iOS, or the IOStream, and we used both syntaxes, do they both run and do the same thing? Or does it
They don't both do the same thing because like this operator does some fancy stuff, but you have to be careful not to introduce a namespace conflict. But no, in general, what do you think IOStream is importing?
the same memory?
Yeah. Remember, the C standard library runs everything, right? IOStream in the back end is most probably still using stdio.h for all of its actual interactions. It's just putting a fancy wrapper on it, right? Question?
If like C++ is basically like C with like objects or sorry, and classes and all that. What is C# add?
It's like that plus the .NET framework. And it's C++ or C# sort of moves the syntax to look a little bit more Java-like. Does that make sense? To be honest, I'm not as much of an expert in C#. I'm more of an expert in C# than C++, but yeah, it's like C# kind of, you know, it's used as a scripting language for a lot of stuff, but anyway. When I was but a lad, the language that they taught you in first year engineering was C#. But you know, that was roundabouts in here when C# was, you know, looked like it was becoming a popular language. So, you know, anyway. Thank you very much for your time and attention, folks. Oh,